Okay, dear students, today we shall discuss the characteristics of the wave. So, in that some characteristics are there. The first one is wavelength. It is the distance between the two successive crests or two successive troughs is called as simply wavelength. It is denoted by the symbol lambda. So, what is the crest? See, the height of the wave is called as the crest and the depth of the wave is called as the trough. So, distance between the two successive crests from here to here. Let us see what does it mean by the wave first, then we go to the definition. Wave means a complete crest. See, from here to here it is called the complete crest, and from here to here it is called the complete trough. So, when you add crest to the trough, then you will get the circle shape. That is called the one cycle. That one cycle is called the one wave. And if you are taking the crest from here, then obviously you have to go up to here, because this much length you left in the case of the crest and the same length you have to cover in the another crest. So, the length of one complete crest and complete trough is called the wavelength. As it becomes difficult every time to consider from here to here, then we take the maximum height of the crest to the maximum height of the another crest, next coming crest, because here we are taking the half of the crest. Here also we are taking the half of the crest, which becomes a complete crest, and it includes complete trough also. That's why we say that the distance between the two successive crests or two successive troughs is called as the wavelength. And its units are centimeters, nanometers, meters, angstrom. That just like length units. We know that 1 nanometer equals to 10 power minus 9 meters. And 1 meter equals 10 power 2 centimeters. So, here if you substitute 10 power 2, you will get the 10 power minus 7 centimeters, 1 nanometer equals to. Similarly, 1 angstrom equals 10 power minus 8 centimeters or 10 power minus 10 meters. Let us see the frequency. So, what does it mean by the frequency? Frequency is nothing but the number of waves that can pass through a fixed point in a unit of time. See, you take the three different points. These are red color one dots represent the point. Let's take three different waves, x, y, z. So, x radiation is coming like this, and y radiation wave is like this, and z radiation wave is like this. And here in the case of the first x wave, only one wave is passed through the fixed point in 1 second of the time. So, that wave is called as 1 cycle per second, because one wave means one complete cycle. And this y, in the case of the y light, more number of waves are passed. Just imagine there are 2 cycles per second. In the case of the Z, 1, 2, 3 are passed. So, we say that 3 cycles per second. So, units for the frequency cycles per second are hertz. 1 hertz equals to 1 cycle per second. Then, what is the relation between the frequency and wavelength? Earlier one, what we discussed. See here, in the case of the first X wave, it is not the X-ray, X wave. Only one wave is passed through the fixed point, because its wavelength is more. See here, length is more, and here length is less. Here it is still less. When the wavelength is less, number of waves passed through the fixed point increase. See here, in the case of the x, only one cycle, y 2 cycles, z 3 cycles. So, we can say that frequency is inversely proportional to the wavelength. And let's try to replace this proportional symbol using the constant c. So, nu equals to c by lambda. The reason to consider this c as the constant in this case is c is nothing but the velocity of the light. All these are electromagnetic radiations which travel equal to the velocity of the light, and velocity of the light value is constant, that is 3 into 10 power 8 meters per second. Hence, we take that particular constant, velocity of the light. And velocity is the distance traveled by a wave in 1 second. See, if a light is traveling from x point to the y point, if the distance is 1 kilometer and if it travels in a second of the time this distance, so we can say that 1 kilometer per second, that is called the velocity. Usually velocity of the light is 3 into 10 power 8 meters per second, means in a second of the time the light travels this much distance. And to calculate this c value, c nu equals to c by lambda, c equals to nu into lambda. Wave number means it is the number of waves that is present in unit length. Here I will take here. So, this is the unit length. All red lines represents unit length from here to from here. And this is the length actually. So, here how many waves are present? 1, 2, 3. here more are there, here still more are there. Means in a unit length, number of waves present depend on the wavelength. When the wavelength increases, number of waves present in the unit length decreases. So that is called the wave number. Wave number is number of waves present in the unit length, which is inversely, it is a inverse of the wavelength. So nu equals to 1 by lambda. When the lambda wavelength increase, wave number decrease. And how this is related to the frequency means, we know that nu equals to c by lambda. It can be written as nu equals to c into 1 by lambda. 1 by lambda means nu bar, so we can write nu equals to c nu bar. And units of the wave number are, lambda units are meters, so if meter comes to the numerator, it becomes per meter. Now let us see the amplitude. Amplitude is nothing but the height of the crust or depth of the trough. So here we have seen this is the amplitude. So the maximum height of the crust or the maximum depth of the trough, this is called the amplitude. So what is the use of the amplitude? It shows the intensity of the light or brightness of the light. Intensity of the light or brightness of the light. See, let us take three different lights, 1, 2, 3. The first one amplitude is more, second one is medium, third one is less. So when the amplitude is more, we say that the first one brightness is more and second one is medium and third one is still less. So when it comes to the brightness or intensity, first is more than second is more than the third one. Now let us see the Planck's quantum theory. So let us discuss the Planck's quantum theory. This theory basically says that energy means light is emitted or absorbed not continuously but only discontinuously. If you take a source, the source always releases energy discontinuously like this but not continuously. So when it is releasing the discontinuously, then it has to come in the form of the small packets of energy. So that small packet of energy, each small packet of energy is called as the quanta. In case of the light, this quanta is called as the photon. So let us see here, the energy of each packet of energy is directly proportional to the frequency. Frequency means, we said already, the number of waves that can pass through a fixed point. When the number of waves increases, automatically more photons will be present in that particular length. When the number of photons increase, automatically we can say that energy of the light also increases. So E is directly proportional to the frequency. And here let us try to replace this proportional symbol using the constant E equals to h nu, where h is the Planck's constant, whose value is 6.626 in 10 power minus 34 joule seconds. So we can try to replace this nu with c by lambda, as nu equals c by lambda, or else 1 by lambda equals to nu bar, so we can write E equals hc nu bar. Usually in Planck's quantum theory, E equals to its energy, which used to give in the form of the watt. 1 watt equals to 1 joule per second, and it may be asked in the case of the power also. Power means energy per second. So here the question is, a bulb emits light of wavelength 4,500 angstroms. The bulb is rated as 150 watt and 8% of the energy is emitted as light. How many photons are emitted by the bulb? per second. So let's try to solve this question. Solution. First of all, you see the information here. They said power. We know that power is equals to energy per second. And here they said 150 watts of the bulb. What equals to? We know that 150 joules per second. And now, therefore, E equals to energy equals to 150 joules per second. Now, energy emitted. Energy emitted as light is equals to, see here, from this 150 watts of the bulb, only 8% of the energy is emitted as light. So, all is not coming out as light, only 8%. So, let us calculate what is the percentage, 8 by 100. So, here we will get only 12 joules of energy is emitted from the bulb as light. Now, we know that energy E equals to, we need to calculate the how many photons. So, that NhC by lambda, and we need to calculate the N value. So, N equals to E lambda divided by H into C. Let us try to substitute all these data here. So, that equals to 12 into 4500 angstroms. This said no wavelength 4500 angstroms. Let convert into the meters, that is 10 power minus 10 meters divided by H value 6.626 into 10 power minus 34 joule seconds into C value 3 into 10 power 8 meters per second. All are SI units. So, N equals to 2.727 into 10 power 19 photons are released from the light. Let us see one more important problem which was asked earlier. So, the second question is, iodine molecule dissociates into atoms after absorbing light of 4500 angstroms. If one quantum of radiation is absorbed by each molecule, calculate the kinetic energy of iodine atom. So, bond energy of I2 is equals to I2 molecule 240 kilojoule per mole. So, this is the question. I will simplify this question to make you more understand. So, as per they said, there is one iodine molecule. You know that iodine molecule, this is I2 molecule. So this iodine molecule dissociates into atoms. So it dissociates into the two iodine atoms, I plus I. After absorbing how much of light? 4500 angstroms of light. So this much amount of energy was absorbed by the iodine, so that the bond between the iodine molecules has been broken, and later they got separated and they started traveling. Now they are asking what is the kinetic energy of each of these iodine atoms, and the energy required to break this bond, they said 240 kilojoules per mole. So what are the things we need to do here first? We need to calculate how much amount of energy was absorbed by the iodine first. This is the energy absorbed. Okay. So within this energy, because here wavelength is given, this has to be converted into the energy form. And afterwards, within this energy, how much energy was utilized by the one iodine molecule to break? This is per mole, not for one iodine. So we have to convert for the single iodine molecule. So energy absorbed minus energy used, consumed, then remaining energy will be used for the iodine for its propagation in the form of the kinetic energy. So first of all, let us do energy absorbed. So solution for this is energy absorbed is equals to, we know that E formula E equals to Hc by lambda. So H value is 6.6 into 10 power minus 34 into C value 3 into 10 power 8 meters per second, divided by lambda value, here it is given in the 4500 angstroms. So we shall take 4500 into 10 power minus 10 meters. So this energy absorbed in this case is equals to the 4.4 into 10 power minus 19 joules. And here this is the energy given in the kilojoules, that too for 1 mole. For each atom, how much amount of energy utilized. So this is the step 1, and step 2 is energy consumed. Energy consumed to dissociate I2 molecule, that is called as what we call as a bond energy. So for each molecule, how much amount of energy was used? So let us take here 240, it was given in the kilojoules, we just converted the joules, into 10 power 3 joules per mole, means divided by the 6.022 into 10 power 23. Then we get the answer per molecule, that is 3.985 into 10 power minus 19 joules per molecule. So single molecule is using how much amount of energy? This much amount of energy to break one bond. Energy absorbed by the iodine molecule is this much, and used by the iodine molecule is this much. So the difference gives the kinetic energy. So kinetic energy of iodine molecule is equals to kinetic energy Ke is equals to energy absorbed initially, that is 4.4 into 10 power minus 19 joules minus 3.985 into 10 power minus 19 joules. So 10 power minus 19 value is same, so that we can take it as a common value. So we get the some value that was approximately 4.15 into 10 power minus 20. See here, this 10 power minus 20 means it will be 0.415 actually. So joules per molecule. So for a single molecule, how much amount of energy it was using? So 4.15 10 power minus 20. But here how many iodine atoms are coming? 2 atoms. So for 2 atoms this is the energy, and for 1 atom how much energy? So kinetic energy for each atom. For each atom is equals to 4.15 into 10 power minus 20 divided by 2. So we get the answer 2.075 into 10 power minus 20 joules per atom. This is the kinetic energy of each iodine molecule. Now let us discuss the photoelectric effect. So according to the photoelectric effect, whenever we take a metal with a clean surface, see this is a metal with a clean surface, and there are so many electrons. Electrons are revolving in this metal. Imagine electrons are revolving. This is the nucleus. So nucleus is with the positive charge and electrons are with the negative charge. So they will be in touch with each other by the attraction force. So to break this attraction force, we need to supply some amount of energy. Imagine, so when you are giving some amount of energy, when light falls on the a clean metal surface, electrons absorb this energy of the light and they try to overcome the nucleus attraction power, and afterwards they come out of the atom. So the electrons thus released are called as simply photoelectrons. Here I need to discuss one definition first. See, there is an attraction force between the electron and the nucleus because they are the opposite charged ones. And to break this attraction force, imagine if I need 5 kilojoules of energy, just only for an understanding purpose I am telling you 5 kilojoules. So if 5 kilojoules of energy is required to break this attraction force, if I am giving the light with 5 kilojoules, so this energy will be absorbed by the electron and it will come out. It will overcome the nucleus attraction force. It can easily come out. If I give only 4 kilojoules of energy and this electron, though it is absorbing this 4 kilojoules of energy, but electron cannot overcome this attraction force, so that it will not come out of the orbit. But the speed of the light increases because it is absorbing the energy. If 6 kilojoules of energy is absorbed, then electron is using 5 kilojoules of energy to come out of the nucleus attraction power. Remaining 1 kilojoule of energy will be utilized for increasing the kinetic energy of the electron. See, if you are giving the 7 kilojoules of energy, then 5 kilojoules of the energy will be utilized by the electron to overcome the nucleus attraction power. Remaining 2 kilojoules of energy will be utilized by the electron to increase its kinetic energy. So basically photoelectric effect says that when a light of certain frequency falls on a clean metal surface, electrons absorb that particular energy of the light and they come out of the metal surface. So this phenomenon is called as the photoelectric effect. In simple way, when light of certain frequency hits the metal surface, electrons are ejected from the metal surface. This phenomenon is also known as the photoelectric effect. So here we set the frequency, the minimum frequency of the light that is required to remove the electron from the metal surface is called as the threshold frequency. Threshold frequency. Threshold frequency is denoted by the symbol nu naught. Okay, and a threshold energy. Threshold energy means the minimum energy required to remove the electron is called as the threshold energy. Threshold energy means if you want to get the threshold energy, frequency has to be multiplied with the Planck's constant, then only you will get the threshold energy. Threshold energy, frequency both are different. So the minimum frequency required to remove the electron from the clean metal surface is called as the threshold frequency, and the energy associated with that particular light is called as the threshold energy. So imagine here we are giving see E1 amount of energy. This is the energy, E1 amount of energy, and threshold energy is E2 amount of energy and remaining energy is kinetic energy. So we can represent the this particular photoelectric effect as E1 equals to E2 plus Ke, where E1 is the energy absorbed by the atom, where E2 is the energy consumed by the atom, that is threshold frequency or threshold energy, and kinetic energy K is the kinetic energy of the ejected electron. This can be written as, we know that E equals to h nu. So that E1 is equals to h nu 1 and E2 is equals to h nu 2. But most of the textbook, they don't take this symbol as 2, but they take it as naught, 0. So in such cases, E naught equals to h nu naught, as I have shown here. So this one can be written as h nu 1 is equals to h nu naught plus kinetic energy. So this is the energy absorbed by the light, this is the energy consumed by the light, this is the kinetic energy of the ejected electron. And this h nu naught is also called as the binding energy, because it is the energy that helps to break this bond between the electron and the nucleus. So some textbooks, they give it as a binding energy also. Even this energy is also known as the ionization energy, because we are removing the electron and making this metal atom as metal ion. So it is also called the ionization energy, and it is also known as the work function, W naught. That's why this photoelectric effect forms can also be written as h nu 1 is equals to h nu naught plus Ke. This is one form. Or else h nu 1 is equals to binding energy plus kinetic energy, or else h nu 1 is equals to ionization energy plus kinetic energy, or else h nu 1 is equals to work function plus kinetic energy. So any of these forms means, if they ask binding energy, you can use this one. If ionization energy they are asking, you can use this particular form. If work function value is given, you can use this particular form. And there is some other related information also regarding this photoelectric effect. Next one here is, so here h nu 1 means we can write the hc by lambda 1, because sometimes they give the wavelength. Here we can write the hc by lambda naught plus kinetic energy. So kinetic energy finally can be calculated as K equals to hc into lambda naught minus lambda 1 divided by lambda 1 lambda naught. So this formula is very helpful in solving the problems based on the photoelectric effect. What other related information is associated with the photoelectric effect? See, how many photoelectrons we can remove from a particular atom, and what is the relation between the number of electrons coming out and the energy of the light that falls on the surface of the metal. See, as I said here, every time when you are increasing the energy of the light that falls on the metal, it is increasing the kinetic energy, but it is not removing the more number of electrons. Though here electrons are there, but 5 kilos, when you send the 5 kilojoules of energy, that is used by only one electron. When we send the 6 kilojoules of energy, that was used by only one electron is coming out, and remaining 1 kilojoules of energy is used for the kinetic energy. And when you send the 7 kilojoules of energy, 5 kilojoules of energy was utilized by the electron, and remaining 2 kilojoules of energy is utilized for its kinetic energy. So when the energy of the electron, when the energy of the incident radiation increases, it increases the kinetic energy of the photoelectron, but it will not remove the more number of electrons. When you want to remove the more number of electrons, what is to be done? You have to send the more number of the waves. So only one wave can remove only one electron, that you have to remember. When more number of the waves you are sending, more electrons will be released. When the number of waves increase, automatically brightness of the light also increase. When the brightness of the light increase, we say that intensity of the light increase. So when the intensity of the incident radiation increase, intensity of the incident radiation, incident light. When the intensity of the incident light increases, it will remove the more number of electrons. So intensity of incident light is directly proportional to the number of photoelectrons. When the intensity increases, it will remove the more number of electrons. But when the energy of the incident radiation increases, it increases the kinetic energy. So energy of incident radiation, incident light, is directly proportional to the kinetic energy of the photoelectron. So those are the some basic information regarding the photoelectric effect. The other related information regarding the photoelectric effect is, as I said just now, when the frequency, see, minimum frequency is required to remove the electron. That is called the threshold frequency. If you are sending a light that is not able to give this minimum frequency, then we cannot see the photoelectric effect. So photoelectric effect cannot be observed in the cases where the frequency of the incident radiation is less than threshold frequency. Then in which cases we can see the photoelectric effect? We can see the photoelectric effect only in the cases where the frequency of the incident radiation either greater than or equals to the frequency of the threshold frequency. So in this condition only we can see the photoelectric effect. Here we cannot observe the photoelectric effect. And which atoms usually show photoelectric effect easily? Photoelectric effect basically says that when light falls, electrons are coming. For this, the ionization energy must be very less in the case of the metals. So when the ionization energy is very less, it is easy to remove the electrons. So then whose metals ionization energy is very less? It is very simple, that alkali metals, because they are the elements with largest atom. So that's why their metallic radius is more, so easy to remove the electron. In that also, cesium is the metal that is able to release the electron easily, so that in most of the photoelectric devices we use this cesium as the metal. If cesium is not available, we use the another metal, that is potassium.